Hello folks, today we're joined by Jarek, one of our very clever engineers from Poland, and is it Łódź or Poznan? Łódź, yeah, lovely city. A lot of our clients in GFT are coming up with challenges and more sophisticated requirements around near real-time data pipelines, and that's because in recent years the pivot towards mobile banking, for example, just mobile computing in general. It means the cycle time to insight has dropped from days to seconds. Increasingly, our clients are having to move away from T+1 batches to near real-time data pipelines. And that's what this minimal viable demo is all about, really. It's to demonstrate some best practice and some points of view about near real-time data pipelines. So, on that note, Jarek, if you could give us a quick just high-level overview of the architecture you've worked on here. I believe it's called TradeLens. Take us a quick one-over, and then we'll sort of deep down into some secret sauce thereafter.
Yes, sure. Okay, so we fetch the data from external website. We load the data into our Kafka topics. Then we consume this data in Spark streaming and Apache Flink. Later on, the data is saved into S3 bucket, which triggers our Lambda function that updates metadata in Hive MetaStore, so that data is cataloged. Dremio uses the data from S3. Additionally, we fetch the static data about companies and put it into SQL database that is also used by Dremio. And we are streaming data from Kafka using Apache data streaming into Elasticsearch. And this part we're going to cover later.
Okay. Thanks for that. A lot of components in play, Jarek. Just taking a step back to the TradeLens data, just give me a bit of a sort of a real-world context of what TradeLens is.
So this is a stock market data. We fetch it using our Dockerized application written in Kotlin. We create about 8,000 WebSocket connections to fetch asks, bids, trades, and tops. Like I said, we also fetch static data about listed companies, its website, its CEO, number of shares.
So if I read that correctly, it's very much a near real-time streaming data source and a reference data source.
Yes.
Okay. It's interesting, and before we get on the architecture a bit further, we talk about Kubernetes here, which is certainly progressing, getting more mature every year and becoming more convenient every year, but it's still not easy, and it's a good example of what we see a lot of our clients moving towards, of infrastructure as code, immutable infrastructure. And it's forced a lot of our clients to think about code and continuous integration pipelines, not just for normal code, but also as infrastructure. So, if we look at this example, what's going on here? Tell me about this Terraform and why Terraform for your infrastructure as code pipeline.
So in Terraform we set up our Kubernetes cluster, so we can automate this. And this is so-called infrastructure as code approach, and we aim for reusable modules in Terraform, so to avoid hard-coded environment specific information. We build a level of indirection.
Right, I see. So what we see in here is the environment-specific information being injected into these variable placeholders, and that's what allows us to have a sort of reusable modular approach to Terraform modules. That makes sense. Certainly I've noticed cloud-native CloudFormation is very prevalent, but also I think Terraform is more prevalent. I think it seems to have a more multi-cloud aspect to it. So it's good to see you using that here. I get a concept of the type of data we're using, and how it's being consumed and put on the Kafka stream. Can you give me? I probably should just take a minute if you're an old timer like myself, you might not be overly familiar with Kafka and why Kafka versus a traditional event bus like IBM MQ. Well, Kafka, he's not so much of a new kid on the block anymore. It's quite mature, but what it does is the same as an event bus. It does the pub sub model very well, so multiple consumers. But it's a tendency to be a bit dumber in that sort of central point, that sort of central point of contention. So whereas in an event bus, it eventually sort of embeds logic and routing logic, Kafka stays quite simplistic at its center, and it sort of pushes that sort of logic into the consumers. So you find the consumers are managing, where they are in that log, where they're up to in terms of data consumption, message consumption, and moving that burden to the consumer just allows for a much more scalable and simplistic approach really with Kafka. So another key difference I think the old timers like myself need to consider is it's a non-destructive DQ mechanism. So if you're consuming a message of a JMS compliant queue, for example, you're going to destroy that message. You won't have to worry about competing consumers. With Kafka, however, you're not going to destroy that message. And one of the benefits of that is you can have a fan out of data, multiple use cases consuming the same data. So a data scientist, an operational data store, or some type of fraud alerting system can all use the same logical piece of data. They don't have to go to the back of the queue and ask for that data. They don't have to ask for a new point-to-point connection. They can just plug in the existing stream. So I think it's important so I get that sort of differentiator of Kafka around. Sorry to interrupt you, Eric, but yeah, do you want to go back and tell us some of the compromises or some of the secret sauce around how you use Kafka? For example, I'd imagine ordering and race conditions are a couple of concerns that a lot of our clients would be interested in.
Yes. We use 4 predefined Kafka topics. These topics are partitioned, like you said. The ordering is not guaranteed, but to have this achieved, you have to use proper key. So, for example, if you want to have your trades processed in a sequence that they arrive on a topic, you have to have trades for a given company placed on one topic, on one partition of that topic. So that way a consumer that is attached to that partition will consume and process these trades in a sequence that they arrive.
Right, okay. So let me try and play that back in my own words. So if Peter spends $10 and then he is paid $10, the net effect is zero. But if those transactions are processed out of date and read out of order, you might see these being $10 up and $10 down conversely. So what you're saying by using tricks around partition keys, I can avoid those types of race conditions by making sure both my $10 plus and negative end up in the same partition and are in order rather than out of order being processed by different consumers. Is that,
yes.
Have I got that right?
Yes,
okay.
Exactly. And partitioning also allows you to split incoming stream into substreams and divide it into multiple servers so that the consumers can process the messages simultaneously, being faster. We do it in Spark Streaming by using many workers. More
parallelization, more throughput, I see. So I see here we've got sort of 2 consumers going on here, and what's not clear to me is, are they doing 2 different use cases, or is this more of a compare and contrast exercise?
These consumers works in different approaches. Spark Streaming uses mini-batch approach, so we have to wait a certain amount of time to start processing these messages, and they are processed in group. While Apache Flink works in a native streaming approach, means that message is processed when it arrives in the system, and there is also a concept of windows that allows you to refer data from a certain period of time.
Right. So, I mean, microbatching is not just exclusive to Spark Streaming. You can achieve that as well.
Yes, but by selecting bounding window, you can achieve the same.
Okay, that's good. Okay, so I sort of get the feeling. I mean, it's perhaps oversimplistic, but if I think throughput and I think latency, that's a couple of differentiators.
Yes.
What's going on here?
So Spark Streaming fetches the date from Kafka message timestamp and use it as a partition column when persisting on S3 bucket. And that's what we have done here in Spark Stream. When a new file is created on S3, it doesn't mean that you can query the data in Athena. That's what you want ultimately to do. So
because at that point in time, it's just a binary bit of information sitting on S3. It's essentially meaningless. So.
Yes. So we have to describe it.
Yes.
And to do this, we can use one of the three approaches. First one is very convenient if you don't know much about the incoming data. You can use glue crawler.
Yes.
It will discover the data, partition, schema, and save the data in about this in Hive McAlister. So you will have the.
So that's the positives. What are the downsides of the crawler?
This is slow and it blocks the table from queries.
It also strikes me as being, well, not really in the spirit of a near real-time data pipeline. You know, it seems to be very retrospective and a bit closer to the world of batch, and you know, there's an issue of trust depending when it's run and when this schema has been inferred. Tell me about the near real-time approach to metadata.
Okay.
And is that what we're looking at here?
Yes. So second approach is to use DDL directly from Athena. You can create an external table, point S3 location, and that's all. You have access to the data.
Okay.
And the third approach is that what we used here. We use Glue API directly from code. So we have Lambda function,
and I think
trigger.
That's the approach I see resonating with our customers, you know, an API-based integration, API-based metadata. Oh, interesting,
Yes.
okay. So we've got the metadata, we're now got the capability for a schema on read. I see Parquet here. What's the story behind that?
This is columnar format of data that is really fast if you are analyzing the data in tools like QuickSight, when you have to group the columns by data by columns.
Does it do anything else? Does it sort of cluster the data? You know, does it order the data within certain boundaries? Presumably, I guess it has to since it's columnar. So would the takeaway be there then, so even though it's S3, it's a binary object, if you use the right format, I mean, just out of the box with the sort of object name, you get a degree of partitioning, date being a good example. And Parquet brings extra read access path capability by, you know, getting a degree of clustering and ordering, and also compression, I suppose, as well. And all that for free without a sort of index or secondary read structure on top. Definitely very useful for a poor man's database, I think. So, Jarek, that's all good so far, but I have to admit, I don't know what this icon means.
This is a QuickSight. So if you are not a tech guy, you can use data from Athena directly in QuickSight. That's what I didn't draw before. So yes, you don't have to know SQL.
Right, okay.
You can query the data and draw charts.
Is it fair for me to put QuickSight in the same sort of bucket as Tableau? Is it attached?
Yes.
Yeah. Okay. So let's talk on to, you know, I know a lot of our clients are, there's a bit of a buzzword here, Apache Arrow. So very keen to understand what's happening here with Dremio and Apache Arrow.
Yes, so Dremio is a data as service platform. It allows you to transform, join data from various sources in one place.
Right, okay.
And it uses...
So it's a logical view over many persistent
Yes, in our case it's, like I said before, it's SQL database, Elasticsearch, and S3 bucket storage that we use in Dremio together. And you can see it on the screenshot. Here.
Looks good. So if Dremio is a sort of the nice sort of federated data lake, you know, the logical layer of the top, what is the secret sauce behind Arrow? You know, what's special about Arrow?
Arrow is a special format. It's very low API mechanism that really speeds up the transforming and processing the data. So the queries that you make in Dremio are really, really fast.
Yeah, interesting. I missed one thing.
Mhm.
Elasticsearch. Did we talk about that? So what's going on here and what's happening here?
So when designing the architecture, we have in mind that we should be as much cloud agnostic as we can.
Yeah.
So that's why you see Dockerized application here. That you see Kafka, Spark Streaming, S3 that can be replaced by HDFS, but we also wanted to add something that is really bounded to AWS. It's Kinesis here, and we stream the data into Kinesis data streams and do some filtering on the data so that we will find anomalies.
That's interesting. So many people would say Kinesis as an event stream is very similar to Kafka, and you could argue they're mutually exclusive, but can you sort of compare and contrast the two, and what drove your decision to use that as a sort of an adapter to Elasticsearch?
It was very convenient for us to use it. So we are using Kafka as our ultimate source of data, and connecting Apache Kinesis, we used Apache Kafka connector with it, and it was very
so
fast.
Really productivity, convenience, the sort of cloud native answer to
exactly. You can scale it really easily.
It's good to see a practical approach. I definitely accept that flexibility and the capabilities, features of Kafka are a lot more so than Kinesis, but it's interesting and very practical to see that for a one-off point-to-point interaction, you've taken advantage of a cloud native service. That's a good thing. It looks good. It's a good application of a near real-time data architecture. You hinted about this topic earlier, and I guess this is my chance to sort of build on the good work that Jarek has talked about. We see a lot of our clients moving to data as a service and data discovery, and the key thing about data discovery is being able to find it. If Bob and Bill are sitting on different floors in the office trying to find the same data, and they don't even know, he doesn't know Bill exists, he doesn't know Bill's already done all the work, all the analysis, wouldn't it be a massive advantage for Bob to know that he exists and he can leverage his work? And the key to that is data lineage. Data lineage allows us to track data across the environment, allows us to know who's using that data. You don't get data lineage until you master near real-time metadata. You can get data lineage for sure that can be stale, get out of date, just like a logical data model can be a year or two out of date and get you in a lot of trouble actually if you hand it to a regulator, even if it's 95% correct. Near real-time metadata, we're seeing increasingly with a lot of our clients, is becoming the secret sauce to establishing data lineage. And data lineage is becoming the secret sauce to enabling data discovery, which is allowing areas of the organization to be a lot faster and quicker in sourcing data and improving data quality. So one thing builds upon another, and you get a nice synergy. And what better time to do all that other than when you're doing your cloud migration. So listen, I'd like to thank you for your time. Jarek, thank you for flying over from Poland to do this. It was a nice talk.
You're welcome.
Yes. See you folks.